Hello, everyone. My name is Clea Sunny. I'm a final year PhD student at Astrocent, and thank you, Julia, for the nice introduction. I'm giving a talk here because I'm a woman in science, like the other speakers here. We followed our passion and we pursued our dream of researching about outer stars and outer space. So, in this talk, I will share my journey in science, and I will talk about how I ended up in researching about dark matter, and I will also give an introduction on dark matter so that you can understand it. And my talk will be followed by Dr. Rita and Dr. Azam, and they will talk about dark matter candidates like WIMS and their searches, and also real life applications of physics. First, a little bit about who I am and what I do. As I mentioned, I'm a final year PhD student working in the experimental sector of dark matter physics. So that means I work with a team who uses underground detectors and photosensors to detect a mysterious matter called dark matter, which I will explain in my later slides. And I will also explain why that is interesting. And I will get back to what I am working on my PhD in the last slides after I talk about dark matter so that it's way easier. So before joining Astrocent, I completed my bachelor's degree in physics, chemistry, mathematics from Christ University in Bangalore in India, followed by a master's degree in physics with a specialization in astrophysics. I was first introduced to the topic of dark matter by when I was searching for a topic for my master thesis. And it was introduced by Dr. Arun Kenneth. He was my then supervisor, who was also who is still working in dark matter. My thesis is a phenomenological study. It's based on the effect of dark matter in red giants. So basically, I looked at how this mysterious or unknown dark matter could affect the behavior of a particular late aging star, which we call red giants. Then later, I published this work in journal right after my post graduation. I was told to keep my presentation inspiring, so I will just talk about how I got inspired in science. Every scientist has a starting point. In my case, my interest in astronomy began when I was in primary school. Long before I started my journey in research or in dark matter physics or in physics, I was just a curious kid because like any other child who, whenever any other child who are so whenever they see the stars or the pictures of galaxy, they get curious and they get so mesmerized. I was also like that, and I also used to have a lot of questions like why sky is blue and why sky is red in the evening, and so on. And have you ever wondered why only some people are interested in science? Because I was thinking about it lately, and I think it's because, or it's based on how one's natural curiosity is encouraged or developed in the childhood. Because in my case, it was my father who encouraged me asking questions. So it's not a particular type of questions. It's the act of questioning, which on something which we didn't understand. I used to have these kids' knowledge magazines or kids' science TV programs, which we are subscribed to, and I think all these triggered an interest in science in me. And then later, I figured out my field of interest during my school time, and I think upper primary school teachers have a major role in it because it's that age of the kids that they are introduced to various core science subjects, and these school teachers, upper primary school teachers, they can easily guide them and spark an interest in them. That's how I got into physics, but because my first physics teacher was super cool. And then later we explored the field of interest. In my case, I used to read a lot of space books. And I was in my seventh grade, and this is how I got into astronomy. And I was reading this autobiography of Yuri Gagarin, who's the first spacewalker. And so when I started reading the book, I wanted to be an astronaut. But in the book, he talks about his struggles during his training for space mission. And he mentioned that he threw up the whole time when he was in a high gravitational chamber during his training. And I thought, I have car sickness, so I cannot be an astronaut. So I completely changed my ambition from being an astronaut to space scientist. So that's all about my inspiring story. I don't know if it was inspiring to you. So I will show you a small video, and this will take you in a journey from Earth through the observable universe. So below at the bottom, you can see it's scaled in distances, in kilometers, so that you can feel the size of the universe. So you can see we are zooming out of Earth, we pass Moon and the planets in the orbits and Sun, and there is a lot of empty spaces in between stars. And it's a chance for us to picture ourselves in the cosmos and appreciate the scale of everything we are trying to understand. This shows how small we are in this vast space and time. And then we see our galaxy, which is a Milky Way galaxy, just one galaxy in billions of galaxies, gathered in clusters and then superclusters to the largest cosmic structure which we have ever mapped, which is the cosmic web. This is just a simulation, but I always find this video very interesting. Okay, let's talk some numbers. Let's discuss what is universe made of. When scientists talk about the composition of the universe, they often show this pie chart, which represents the total energy density of the universe, and which means it's the total energy budget of everything that fills the space. So here you can see the visible matter is just a 5%. It's a tiny slice of the pie chart. And this visible matter includes me, you, the stars, galaxies, and everything that is made of particles which we are familiar with. And a huge chunk of the pie chart is dark energy, which is some mysterious energy which we don't know much about, but we know that it drives the accelerated expansion of the universe. You might have heard of it. And then we have a significant chunk, which is something called dark matter. We don't know what that is. It's literally dark. We cannot see it. It doesn't interact with light. But we know the presence of some unseen matter from its effect on other astrophysical phenomena. And I will talk more about it starting from next slide. But it's so amazing and humbling to realize that whatever we know, everything what we know is just in this tiny slice of 5%, and that is not yet fully understood. We have yet to be that is yet to be explored. Okay, so let's talk some dark matters. The first clue of dark matter was given by Swiss astronomer Fritz Zwicky in the 1930s when he was studying coma cluster. So a coma cluster is a galaxy cluster, and a galaxy cluster is a group of around 5% of galaxies and around 15% of gas and almost 80 to 85% of galaxy cluster is dark matter, but we don't know that yet. Yeah, I mean, I will get to it. So he was studying this coma cluster when he noticed something strange. He noticed that the galaxies in this cluster are moving at a speed much higher than he was expecting. And at this rate, at this speed, the galaxies should have flown apart, leaving the cluster behind, but they didn't. So imagine we have a merry-go-round with kids on it. If it spins too fast, the kids should fly away, right? But if the kids are well secured in the seats, they should be staying there. So that was the basic idea behind it. And Zwicky concluded that there is some massive amount of matter that is providing some extra gravity to these galaxies, to keeping them in the place, to keep them holding together in the cluster. And he called it dunkle materie. So he coined the term dark matter, and hence he is known as the father of dark matter. And building on the Zwicky's observation in invisible matter in the galaxy clusters, in the 1970s, it was American astronomer Vera Rubin. She looked at independent spiral galaxies. It's a type of galaxy. And she measured the the stars orbiting around the galactic center, for example, this galaxy. So this is what we call a galactic flat or rotation curve. So she measured the how stars are orbiting around the galactic center, and she expected that the stars in the outer galaxy they should move more slowly compared to the inner ones because there is more gravity. There is more visible matter there, hence more gravity. But surprisingly, the outer stars were spinning or moving as fast as the inner ones. So she concluded that there is something massive to provide these galaxies, sorry, stars, the gravity, and then keeping them in their places. So she coined the term, or she mentioned it as non-luminous matter, and this is the first evidence for the strong evidence for dark matter. And I want to talk a bit more about Vera Rubin because she is one of the female pioneer in dark matter. She faced career-long struggles with institutional sexism. She was denied access to top universities such as Princeton for graduate programs. She was denied access to Palomar Observatory, and then later she was the first women observer at that observatory. She pushed equality in astronomy and she reported against discrimination in pay gaps between men and women with the same qualifications, lower pay for married women, etc. And she is actually inspiring to all of us because it's because of these female pioneers like her and her candor in sexism that I get same wage as my male colleagues. So I think in this events like female empowerment, I think we should get inspired by these kind female pioneers. Okay, moving on to other compelling evidence of dark matter. Let's start with the gravitational lensing. So, gravitational lensing is more like a tool than it's an evidence because it can map the all the kind of mass in a space and even including the dark matter as well. So, I will explain what is gravitational lensing. So, uh, let's imagine we have an observer in the from Earth, and we are looking at a distant object, a distant galaxy, let's say. And if we are seeing that distant galaxies image as multiple distorted magnified images, that means there is something massive in between the line of sight between the observer and the distant galaxy. That is, and that mass has so much gravity that is bending the light that comes from the distant galaxy. So this effect is called gravitational lensing. As you can see, this is a real picture. You can see from the this is a galaxy cluster and this is gravitational lensing effect. So this lensing, we can reconstruct the 2D map of the mass distribution, and we can see if there is any unseen matter there. And then coming to bullet clusters is when two galaxy clusters collide with each other. And we know that galaxy clusters has only a 5% of galaxies, so it's collisionless. And we have gas that interact with the other gas. So when galaxy clusters collide, these galaxies just pass through, and the gas at the center, the collision site, they will interact. So when we use gravitational lensing to map the mass distribution, we saw that most of the mass were with the galaxies because it's just 5%. So we are not expecting that it to be there. But we saw mass peaking at these galaxies. So that's how we know that there should be some unseen matter to provide that much mass distribution there in the along with the galaxies and not with gas. So yeah, and then we know that if dark matter is there, that is collisionless as well because it didn't interact with anything else. Some other evidence is large scale structure formation and cosmic microwave background radiation, which I want to talk more about it, but I don't have time. But these evidences say that without dark matter, the structures which we see in the current cosmos that shouldn't be forming because without the dark matter there is not enough gravity to clump matter together to form structures in the very early universe. So with all these evidences we can say what is dark matter or what the properties of dark matter is. It neither emits light, it doesn't absorb light or it interacts with any radiation. it gravitationally interacts. We know that from gravitational lensing and the flat rotation curves. It's cold. By cold, we mean it's heavy. The dark matter particle is heavy. It should slowly move. It shouldn't move at the speed of light because it has to move slowly so that it can clump and form structures. From the current precise measurements of the abundance of light elements such as hydrogen, helium that formed during Big Bang, we know that the dark matter has to be non-baryonic, and also dark matter is survived from early universe until today. So we know that it's stable, it's long lived. And then, so we have these properties. So we check if we have any known particles in the current universe that can match these properties. So we have a framework of fundamental particles, which are electrons, protons, whatever elementary particles which we know, and the forces between them. That framework is called the standard model of elementary particle. And we checked if we have any such particles which we are familiar with. But no known particle in the standard model can explain all these properties at once. So we can assume that if dark matter particle exists, it could be from beyond the standard model, a particle which we are not yet familiar with. And based on that, we have some possible dark matter candidates, such as weakly interacting massive particles or WIMPs, axions and sterile neutrinos, etc. And my PhD focuses on low mass WIMP search. So I look for these low mass WIMPs in detectors. So that's all for dark matter. But before I wrap up, I just want to say that how cool is it to be a scientist or astrophysicist? Because there are a lot of perks. And one small one is that whenever I I tell someone that I work in the astrophysics field, they are often amazed, and it's a feel good moment for me because it's astrophysics and it's so cool. And another main thing is that we are following our passion because we are not fall in this career because we need just money. We are in this field because we chose that field. We are in the science field because we want to research about it, and it gives content, right? Because I am working on something I truly it's exciting. So it's something that is worth noting. And there is another thing that it's always challenging because it's science and you get problems every now and then. And it's stressful, but it's challenging and hence you never get bored. And the main perk for me is the international trips because I didn't know that I would travel this much when I joined for PhD. But it's all for collaboration, research works. And yes, we do research work in these travels, but it's still nice that you are seeing places because and guess what? It's completely free. So it's actually a very nice field if you like traveling and if you like science. That's all. That's all. If you just if you follow your curiosities, because that's where discovery begins. So just follow your curiosities. That's all. Thank you.